Río Hurtado Valley, Chile. The 1st of July 2025. 5 hours, 15 minutes, 11 seconds universal time. The sky above the high desert is moonless and dry, and the air has the particular stillness of a place that was chosen for it. The valley lies in the foothills of the Andes, at an elevation of 1,700 meters, in a region where the rainfall stops for most of the year, and the seeing conditions are some of the best on Earth. There is a small dome on a ridge here. Inside it sits a half-meter Wright-Schmidt telescope. It belongs to the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, a NASA-funded survey program that scans the visible sky each night for objects that move. The telescope has just opened the next of its routine 30-second exposures. It is one of thousands the system will record before dawn. The data is automatic. The software is patient. Most of what the cameras see on most nights is nothing. The cosmos is mostly empty. The exposures fill, the disks spin, the pipeline reduces, and the system goes to bed by sunrise. This is what survey astronomy looks like in the present tense. Quiet, repetitive. The interesting thing happens once every few years. This exposure contains a streak. The streak is short, it is faint. Magnitude 17.8 in the O-band filter, which is the survey's red-orange channel. The streak is one of perhaps 400 objects flagged in the catalogue that night, most of which will resolve into known asteroids, known comets, satellite glints or noise. The streak is in the constellation Sagittarius. The streak has not been recorded before. The streak is moving at a rate that does not match anything in the existing tables. It is moving at 87,000 kilometers per hour relative to Earth. The asteroid center has not been notified. The automated pipeline has assigned it the temporary designation A11PL3Z. The pipeline has not assigned any meaning to that velocity yet. Larry Deno, senior software engineer and astronomer on the ATLAS team, is at his desk at the Institute for Astronomy at the University of Hawaii at Manoa. It is afternoon there, 8,000 kilometers from Chile. He is reviewing the previous night's flagged candidates. He's doing what he has done thousands of times. He's looking for something that does not yet have a name. He does not know, sitting at his terminal that afternoon, that he is looking at the third confirmed object in human history to enter our solar system from another star. He does not yet know that the streak is older than the sun. He does not yet know that it has been travelling, in a straight line bent only by distant gravity, for somewhere between 3 and 11 billion years. Tonight we are going to walk through this slowly, fellow night watcher. You do not need to hold every number. Some of them will stay with you. The rest can pass. The object in this story will leave the solar system forever, and it will not come back. And the light from its surface has been arriving at our telescopes for many months now. We have time. The photons are patient. They have come a very long way to be here. Let us begin where the physics begins. The first thing to understand about 3i Atlas is that it should not have been findable. The cosmos is enormous, and our solar system is small, and the chance that a wandering object from another star will pass through the inner planets in any given decade is so low that for almost the entire history of astronomy, we did not see one. We did not know they existed. We could only predict from the dynamics of stellar systems being born and dying across the Milky Way that they had to. Every planetary system that ever formed must have ejected debris. Every red giant must have stripped its companion of icy bodies. The disk of the galaxy must, by simple inventory, contain trillions upon trillions of small ice and rock objects loose between the stars. They are not pulled by any sun. They drift. They cross. Most of them never come close enough to any other star to be observed. The first one we ever found was on the 19th of October 2017. The instrument was a 1.8-meter Pan-STARRS telescope on the summit of Haleakala in Maui. The observer was Robert Werrick, then a postdoctoral researcher at the Institute for Astronomy. The object was elongated, dark, tumbling and dry. It was given a name in Hawaiian, Oumuamua. It means a scout or a messenger, arriving first. We watched it for less than 3 months. By January of 2018, it was too faint to follow. It is now well past the orbit of Neptune, travelling toward the constellation Pegasus, and we will never see it again. The second one was found on the 30th of August 2019 by an amateur astronomer named Gennady Borisov, observing from Crimea with a 0.65-meter telescope he had built himself. The object was a comet, fully visible, with a tail. It looked to telescopes much like comets we had seen before. It crossed perihelion in December of 2019. It carried the designation 2I Borisov. The 2I prefix is the Minor Planet Center's way of saying second interstellar. The third one was found at 05:15:11 Universal Time on the 1st of July 2025 in Chile. It received its designation a day and a half later, the 2nd of July 2025, 21 hours, 31 minutes UTC. Minor Planet Electronic Circular, 2025 N12. The full name is 3I Atlas, with the parenthetical cometary designation C/2025 N1. The 3I prefix means third interstellar. 2 years between the first and the second. 6 years between the second and the third. The cadence is meaningless statistically. There is no rhythm. There is only the slow filling of a counter that began at 0 in October of 2017 and may, in the next decade, climb into the tens. Let us hold this for a moment. For the entire span of recorded astronomy, from the cuneiform tablets of the Milky Sky catalogue 3,000 years ago, through Tycho Brahe and Edmund Halley, and Charles Messier, and Caroline Herschel, through every great cataloguer who ever wrote down the position of a comet, we believed every comet we saw belonged to our sun. They were our property. They had been made in our nursery, condensed from the same disk that made Earth and Mars and Jupiter, around 4.5 billion years ago. The icy bodies of the Oort cloud, the dirty snowballs that swing in from the dark every few centuries and burn off a tail and return, were ours. Carl Sagan called them long-period comets, and he wrote in 1985 that they were the most ancient and least altered samples of the early solar nebula we would ever touch. He was right about that. He was wrong about the boundary. The boundary broke in October of 2017. By July of 2025, it had broken 3 times. What this means, and the physics tells us this clearly, is that the cometary inventory of our cosmic neighbourhood is not just ours. It is everyone's. Every star in the Milky Way that ever made planets ejected debris. The galaxy is full of these visitors. We have only just learned to see them. The instrument that saw 3I Atlas first was not pointed at it. The Atlas survey was not designed. In 2015, when its first telescope went up on Haleakala to find interstellar objects, it was designed to find rocks coming toward Earth, specifically near-Earth asteroids in the size range that could destroy a city. The acronym Asteroid Terrestrial Impact Last Alert System gives you the original mission in a single sentence. Atlas is a watchman. It scans the sky every night, twice over, in fast cadence, looking for things that could hit us. Its great virtue is not depth. Its great virtue is coverage. It sees the whole visible sky every couple of nights, and its photometry is good enough to catch moving objects at magnitude 19 or brighter. What this design accidentally produced by the year 2025 was a near real-time map of every bright thing moving anywhere in our hemisphere of sky. The Chilean telescope at Río Hurtado, observatory code W68, had been operating since 2022. The Hawaiian telescopes had been operating since 2015. The South African telescope at the Sutherland site had come online in 2022. Together they cover the entire celestial sphere on a roughly daily cadence. When 3I Atlas slid through the field of view of the Río Hurtado telescope in the early morning hours of July 1st, it was caught not because anyone expected it, but because the survey catches everything that moves at magnitude 17.8 or brighter and is not on the catalogue of known objects. The system did its job. The streak appeared in the morning's report. It went into the queue. By the next day, the orbit was being refined. The person who did most of the refining was Marco Micheli of the European Space Agency's Near-Earth Object Coordination Centre in Frascati, Italy. Micheli had spent 15 years doing this kind of work. He had calculated orbits for thousands of newly discovered objects. He knew what the residuals looked like for a bound asteroid. He knew what they looked like for a Jupiter family comet. He knew, within minutes of fitting the early data points, what they looked like when the answer was a hyperbola. A hyperbola is the mathematical shape of an unbound trajectory. If you throw a stone into the air, its path is a piece of an ellipse. If you throw it harder than the Earth's escape velocity, the path opens into a parabola. If you throw it harder still, the path opens further into a hyperbola. The thing about hyperbolic orbits is that they do not close, they do not return. The object enters once, swings around the central body, and leaves forever. carrying with it a quantity called the hyperbolic excess velocity. That number tells you how fast the object was moving with respect to the Sun before it ever felt the Sun's gravity. The hyperbolic excess velocity for 3I Atlas, refined over the following weeks by Davide Farnocchia at the Center for Near-Earth Object Studies at the Jet Propulsion Laboratory, came in at about 58 kilometers per second. This is the largest hyperbolic excess velocity ever measured for any object passing through our solar system. For comparison, Oumuamua, the first interstellar visitor, had a V of 26 kilometers per second. Borisov had 32. 3I Atlas came in twice as fast as one and nearly twice as fast as the other. Translated into the language of galactic motion, this is the speed of a body that belongs to a stellar population orbiting the Milky Way's center in a way that is significantly different from our Sun's. Matthew Hopkins and Chris Lintott, working out of the Department of Physics at the University of Oxford, would publish a paper a few weeks later. They had a model. They called it the Ōtautahi-Oxford model, after their two home institutions, one in New Zealand and one in England. The model takes the velocity of an interstellar visitor, fits it against the kinematic signatures of the various stellar populations of the Milky Way, and returns a probabilistic age. They ran it for 3I Atlas. The answer came back 7.6 billion years at the low end, 14 billion years at the high end. 68% confidence. The universe is 13.8 billion years old. Consider the scale. The Sun is 4.5 billion years old. The Earth, slightly less. The first complex multicellular organism on Earth is something like a billion. The first eukaryotic cell, perhaps 2. Every history book and every fossil bed and every layer of rock that anyone has ever named falls comfortably within the last 5 billion years of cosmic time. 3I Atlas, by the Oxford model's central estimate, was already old when our Sun was a knot of gas in a different molecular cloud. The chemistry of its surface was set in a planetary disk around a different star, in a region of the galaxy whose stars are now scattered across thousands of light years and whose original neighbourhood no longer exists. The object that would cross our sky in October of 2025 carries the memory of a planetary system that has, in all likelihood, already died. This is what was sitting in Larry Deno's queue on the afternoon of July 1st, 2025, as he scrolled through the catalogue of moving objects and saw a streak in Sagittarius he could not place. He did not know any of this yet. He only knew that something was off. The first action Deno took, after pulling up the streak and looking at the numbers more carefully, was to submit it to the NEOCP. The Near-Earth Object Confirmation page, hosted by the Minor Planet Center at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, is the clearinghouse for newly flagged moving objects whose orbits have not yet been independently confirmed. When something appears on the NEOCP, the global and astronomical community gets the coordinates, the predicted ephemeris, and a short window in which professional and amateur observers around the world can choose to point their telescopes at the same patch of sky and confirm the orbit by adding more astrometric measurements. The temporary designation A11PL3Z went into the page on the afternoon of 1st July 2025. Within hours, follow-up observations began arriving from telescopes on 3 continents. The orbit determination work fell mostly to Marco Micheli at the European Space Agency's Near-Earth Object Coordination Centre in Frascati, just southeast of Rome. Micheli had built or refined orbits for tens of thousands of newly discovered objects in his career. The software he uses is called Find Orb, written by Bill Gray of Project Pluto, and a complementary tool called OrbFit, developed by a consortium based at the University of Pisa. Both packages can take a small handful of astrometric measurements and fit Keplerian orbital elements with confidence intervals. For most newly flagged objects, the orbit converges quickly into something familiar: an asteroid in the main belt, a Trojan, a Centaur. The residuals, the small disagreements between observed and predicted positions, are typically 1/10 of an arcsecond or less, and the eccentricity comes back somewhere comfortably below 1. For 3I Atlas, the residuals would not close on any bound orbit at all. Micheli ran the fit. He added more data points as they came in from European telescopes, from observatories in Arizona, from the Canada-France-Hawaii telescope on Mauna Kea. The eccentricity kept rising, past 1, past 2, past 3. By the early hours of 2nd July, the FIT was converging on an eccentricity of about 6. This is a number that needs sitting with. Almost every hyperbolic orbit ever observed in our solar system has had an eccentricity just barely above 1. Say 1.001. Say 1.004. These belong to comets whose elliptical orbits were perturbed during a close pass by Jupiter or Saturn, gaining just enough kinetic energy to escape on the outbound leg. They were bound objects that became, briefly, unbound on their way to the stars. The solar system's previous record holder for hyperbolic eccentricity was a comet called C1980 E1 Bowell, discovered by Edward Bowell at Lowell Observatory in February of 1980, which left on a trajectory of about 1.057. Atlas came in at 6.14135. By the afternoon of 2nd July, the orbit fit had become unambiguous. There was no astrometric model in which this object had ever been bound to our Sun. Its trajectory was the entry and exit of a body that had been moving in a straight line through interstellar space, fallen into the Sun's gravity, made one swing, and would leave forever. At 21 hours, 31 minutes UTC on 2nd July 2025, the Minor Planet Center issued Minor Planet Electronic Circular 2025 N12. The MPEC is a brief document, a few hundred words. It contained the new designation, the early orbital elements, the astrometry, and a single load-bearing line. The orbit of this object is unmistakably hyperbolic, and it is therefore the third confirmed interstellar object. The temporary name A11PL3Z was retired. The catalogue name 3I Atlas, cometary designation C/2025 N1, was assigned. That evening, telegrams went out. Email lists buzzed. A small worldwide community of perhaps 300 or 400 professional astronomers who work on small bodies, and on interstellar objects in particular, knew within hours of the MPEC that the third one had arrived. Karen Meach was one of them. She had led the team that wrote the original Nature paper on Oumuamua in 2017, a paper titled, with a bluntness uncharacteristic of the journal, A Brief Visit from a Red and Extremely Elongated Interstellar Asteroid. It was published on the 20th of November 2017. Meach, Robert Werrick, Marco Micheli, and 23 other authors. She had spent the 8 years between that paper and this moment hoping, more or less openly, for a third object. The first had been hard. It had been faint and tumbling and gone in months. The second, Borisov, had been easier. A real comet, well-behaved, observable for many months past perihelion, but still small, still fading. The third, she would say in later interviews, with the Institute for Astronomy News Service, would be the best of all of them, brighter than the first, slower moving than either, and crucially, more distant from Earth at every point of its passage than 2I Borisov had been, which meant it could be observed for far longer. By 3rd of July, the first spectroscopic observations were already being taken. Cyrielle Aupetom of the University of Edinburgh and the Royal Observatory at Edinburgh was leading a team using the MUSE instrument, the multi-unit spectroscopic explorer, on the Very Large Telescope at Cerro Paranal in northern Chile. MUSE is what astronomers call an integral field spectrograph. It does not collect light from a single point on the sky. It produces a small data cube, 300 by 300 spatial pixels, each one with its own optical spectrum. The result is a map of the sky in both space and colour at the same time. She pointed it at 3I Atlas. The data cube came back. The spectrum was red. The slope was 18% per 1,000 angstroms, give or take 4. The result would be published in monthly notices of the Royal Astronomical Society Letters, volume 544, page L31, in a paper titled Snapshot of a New Interstellar Comet. 3 on my eye. Atlas has a red and featureless spectrum. What does it mean for a spectrum to be featureless? It means that the light coming back from the object showed no sharp absorption or emission lines from any specific molecule, no clean methane band, no water ice ridge, no characteristic dust silicate signature. The light was simply reddened by the surface in a smooth, unstructured way. This is the kind of reddening you get from surfaces that have been processed for a long time by something like ultraviolet radiation or galactic cosmic rays, or both. This kind of red, featureless spectrum is not unprecedented. Some of the most reddened trans-Neptunian objects in our own Kuiper belt look similar. They have spent 4.5 billion years sitting in deep cold, irradiated by cosmic rays, slowly building up an organic-rich processed crust. There is a term for this. It is called space weathering of icy bodies. The red colour is a fingerprint of long, slow, accumulated radiation damage. For 3I Atlas, the reddening implied something specific. The object had not arrived pristine from the disk of some young star, freshly ejected. It had been weathered for a very long time, long enough for galactic cosmic rays to have chemically altered its outer layer, long enough, in fact, that by January of 2026, a team led by Cesare Maggiolo would publish a paper in Astrophysical Journal Letters, volume 996, page L34, titled Interstellar Comet 3I Atlas, Evidence for Galactic Cosmic Ray Processing, in which they argued that the outer 15 to 20 meters of the object's crust had been chemically altered by billions of years of cosmic ray bombardment. It would be the first direct observational evidence anyone had ever obtained of a cosmic ray irradiated outer layer on any small body in the galaxy. But that paper was 6 months in the future. In those first days of July 2025, the only thing the spectrum said clearly was this: the object is old. The orbit said it. The velocity said it. Now the chemistry said it. Now let us pull back. Let us look at where this object had been hiding in the weeks and months before any of us knew that it was there. When astronomers find a new object on its way in, one of the first things they do is search the archives. Telescopes across the world generate enormous quantities of imaging data every night. Most of those exposures contain things no one has yet looked at carefully. If the object you have just discovered is bright enough, and if your orbit is good enough to predict where it would have been in the past, you can run the prediction backwards. You can find faint streaks in old images, in archives spread across satellites, and observatories on 3 continents. This process is called precovery. It is a small, careful, painstaking art. Each new data point in the past tightens the orbit and pushes the trajectory into sharper focus. For 3I Atlas, the precovery search began within hours of the MPEC announcement. The first results came back quickly. The Zwicky Transient Facility, operating from the Palomar Observatory in Southern California, observatory code I-41, had recorded the object on the nights of 22 through 29 May 2025. The frames were faint. The streak was at the edge of detectability. But it was there. The Weizmann Astrophysical Observatory in Israel, code M01, had captured it on 21st May 2025. And then, in the most quietly remarkable precovery result of all, a team led by Davide Farnocchia at the Jet Propulsion Laboratory searched the data archives of TESS. TESS is the Transiting Exoplanet Survey Satellite. It is a small spacecraft in a highly eccentric Earth orbit. It does not look down at the Earth. It looks outward, into deep sky. It stares at a single large patch of sky for roughly 27 days at a time, recording the brightness of every star in the field at 30-minute and 10-minute cadence, watching for the tiny brightness dips that mean a planet has just crossed in front of its host star. It is, in the language of survey astronomy, a photometer. It does not produce sharp images. The pixels are 21 arc-seconds on a side, which is enormous by professional standards. But it sees the same patch of sky with extraordinary photometric stability, week after week. Farnocchia and his collaborators ran the predicted 3I Atlas trajectory backwards into the TESS archive. They found the object in TESS sector 92. The earliest detection was on 7 May 2025. The magnitude was 20.83. By late May, it had brightened to 19.28. The paper, titled simply Precovery Observations of 3I Atlas from TESS, appeared in Astrophysical Journal Letters, volume 991, page L2. What was the object doing on 7 May 2025? It was about 6 astronomical units from the Sun. That is roughly the orbital distance of Jupiter. It was inbound. It was moving at high speed. And, the TESS photometry showed, it was brightening more than its decreasing distance alone could explain. A bare rock, or a frozen body, that is simply being illuminated by the Sun follows a precise mathematical relationship. Its brightness as it falls inward rises with the inverse square of its distance from the Sun and the inverse square of its distance from the observer. If the object is silent, dark, and inert, you can predict its light curve to high accuracy. Atlas was brighter than that, by a meaningful margin. What this means is that the object was already at 6 AU from the Sun, releasing material from its surface. Gas, dust, something. Even at the orbital distance of Jupiter, where our own solar system's native comets typically remain quiet and dark, this visitor was waking up. The surface temperatures at 6 AU are around -170 degrees Celsius. Water ice is hard as granite at those temperatures. It does not sublimate, but carbon monoxide does, and carbon dioxide does at slightly higher temperatures, deeper in. The TESS precovery was telling us something that no one would fully understand until August of 2025, when the James Webb Space Telescope turned its instruments toward 3I Atlas. The object was venting carbon dioxide, already, long before it had warmed. Let us hold this for a moment. On 7th May 2025, a small space telescope in Earth orbit, designed to find planets around other stars, recorded the brightness of a faint streak in its photometric data. The streak was near the limit of TESS's sensitivity. The data went into the archive. The mission continued. No one noticed. The object that produced that streak had crossed into the solar system weeks earlier, somewhere out near the orbit of Jupiter, on a trajectory whose final shape had been determined billions of years earlier by gravitational dynamics inside another planetary system. By 7th May, the heat of our Sun, faint though it was at that distance, had begun to warm the visitor's surface. Frozen carbon dioxide, locked into its crust for somewhere between 3 and 14 billion years, was starting to sublimate. Molecules that had not seen a star up close since their parent system died were leaving the surface, one by one, into the vacuum of our particular corner of the galaxy. The photons that came back to TESS had to do this, reflect off the dust and gas streaming from 3I Atlas, travel between 5 and 6 AU to Earth orbit, strike a CCD detector behind a small primary mirror, on a satellite whose mission was to look at other stars entirely. The detector recorded them, the pipeline reduced them, the archive stored them. No one looked. For 7 more weeks, the object continued to fall inward. It brightened by more than a full magnitude as the TESS sector rotated out of view in early June. It moved into the field of ZTF at Palomar, and ZTF caught it on those late May nights. It continued in. It crossed 5 AU, it crossed 4. The brightness rose with the gentle exponential of an object whose volatiles were warming under a strengthening sun. On the 1st of July, it crossed into the field of view of the Atlas telescope at Rio Hurtado. And finally someone looked. It was Larry Deno. This is what science actually looks like, fellow night watcher. Not a sudden alarm. Not a single dramatic moment. It is a long, slow accumulation of pixels in archives spread across satellites and observatories on 3 continents, with the photons arriving in advance of the realization, and the realization arriving at last on a desk in Hawaii on a quiet afternoon, weeks after the object itself had already been writing its own discovery into our data. Now let us look at what those photons would tell us next. What 3I Atlas would tell us next required bigger instruments. The Atlas telescope at Rio Hurtado is 0.5 meter in diameter. The VLT Muse observations were on an 8-meter dish, but they were quick snapshots, designed to give a first spectrum, not to resolve the object, to actually see the comet, to get a picture of its nucleus and the structure of its coma in fine detail, the most expensive astronomical instrument humanity has ever put above the atmosphere needed to look at it. On 21st July 2025, 20 days after the Minor Planet Center had released MPEC 2025 N12, the Hubble Space Telescope turned on its Wide Field Camera 3 and pointed at 3I Atlas. The observations were led by David Jewett of the University of California, Los Angeles, in the Department of Earth, Planetary and Space Sciences. Jewett has worked on small bodies for nearly 5 decades. He was one of the co-discoverers of the Kuiper Belt in 1992. He has in some sense spent his career building the modern picture of the outer solar system. When the first interstellar object arrived in 2017, Jewett led one of the early Hubble campaigns on Oumuamua. When the second arrived in 2019, he led one of the early campaigns on Borisov. With the third object now in the inner solar system, the pattern was clear. He led the Hubble campaign on 3I Atlas as well. What Hubble saw, even at 3.6 astronomical units of heliocentric distance, was a comet with a clearly resolved coma and a nucleus that remained unresolved, a single bright point source buried in haze. The paper by Dewitt and his collaborators appeared in Astrophysical Journal Letters later in 2025. The key constraint was on the size of the nucleus itself. Whatever solid body sat at the center of all this dust and gas could be no larger than 2.8 kilometers in radius. A later, more refined extraction by Man Tahoe and collaborators, published in early 2026, would bring that number down further. The nucleus, that single ancient body that had carried all of this material out of its parent star system and across the galaxy, was 1.3 kilometers in radius, plus or minus 0.2 of a kilometer. Hold this number for a moment. A solid object smaller than the city of Edinburgh, smaller than the island of Manhattan from end to end. A piece of frozen material, perhaps 4 billion years older than the Sun, that had crossed the galaxy as a slow, dark, silent shape, and had now been imaged by an instrument in low Earth orbit, peering through its diffraction limit at a point 1 billion kilometers away. The mass, derived from the size and an assumed density of frozen ice, came out to approximately 4.4 times 10 to the 10th kilograms, 44 billion kilograms. In more human terms, roughly the mass of a small mountain. Less, in fact, than the cargo handled by the port of Rotterdam in a single year. This is what was crossing the galaxy, a frozen hillside. Now the next thing to look for was chemistry. On 20th July 2025, between the first Hubble imaging and the bigger surveys still to come, a team at the Very Large Telescope detected something unexpected in the spectrum of 3I Atlas. Atomic nickel. This is unusual but not unprecedented. Nickel had been detected in cometary atmospheres before, but typically only in comets approaching very close to the Sun, where surface temperatures are high enough to vaporize metal-bearing dust grains. The detection of atomic nickel emission at 3.6 AU, where temperatures should be far too low for simple metal sublimation, suggested something specific. Carbonyl complexes, molecules in which a single nickel atom is bonded to several carbon monoxide molecules, forming a small, volatile compound that can release nickel slowly, even at very cold temperatures. The same kind of chemistry that operates in industrial nickel refining on Earth. What 3I Atlas was telling us through this faint and narrow emission line was that its surface chemistry was unusually rich in mobile nickel. A signal that, like the red colour, suggested deep processing. Something had been happening to this object, very slowly, for a very long time. But the real chemistry revelation was still 2 weeks away. On the 6th of August 2025, the James Webb Space Telescope turned its near-infrared spectrograph toward 3I Atlas. JWST is the most powerful telescope humanity has ever built. It sits at the second Lagrange point, a gravitational saddle 1.5 million kilometers behind the Earth, where it floats in permanent shade behind a 5-layer sunshield the size of a tennis court. Its primary mirror is 6.5 meters of beryllium, gold-coated, segmented into 18 hexagonal panels. The light it collects has been gathered over a surface area more than 5 times that of Hubble, and its sensitivity in the near-infrared is unmatched. NIRSpec, the instrument used that morning, can split the light of a faint object into its constituent wavelengths, between 0.5 micron and 5 microns. This is the range in which most volatile cometary molecules, water and carbon dioxide and carbon monoxide and methane, have their strongest fingerprints. NIRSpec was, in essence, designed for moments like this. The lead investigator for the observation was Martin Cordiner of NASA's Goddard Space Flight Center and the Catholic University of America. Cordiner has spent his career studying the molecular chemistry of comets and the interstellar medium. The program scientist was Stephanie Milam, also at Goddard, who had coordinated JWST cometary observations since the telescope's commissioning in 2022. What the spectrum returned was a result that would, in the months to come, be argued over more than almost any other measurement of 3I Atlas. The coma of the object was dominated, overwhelmingly, by carbon dioxide. Water was there, but it was a minor component. Carbon monoxide was there, also minor. Carbon dioxide outweighed water in the gas surrounding the nucleus by a ratio of 7.6 to 1. For context, in comets native to our solar system, the typical CO2 to water ratio is somewhere between 1/10 and 1/5. Carbon dioxide is usually a minor volatile, present but secondary to water. Even in the highest CO2 comets ever recorded in our own system, The ratio rarely exceeded 1 to 1. I-Atlas was at 7.6 to 1. This is the highest CO2 abundance, relative to water, ever measured in any comet, anywhere. The result was published by Cordiner and his collaborators in Astrophysical Journal Letters, with the preprint posted to the arXiv server as paper number 25, 08.18209, and the result was statistically robust at 4.5 sigma, above the trend line of all known cometary measurements. The question this opened was twofold. The first, simpler question. How can you make so much carbon dioxide in a single small icy body? The second, harder question. What does this say about where 3I Atlas was born? There are two leading explanations, both proposed in peer-reviewed papers in the months that followed. They are not yet reconciled. The first explanation comes from Cesare Maggiolo and collaborators in their paper in Astrophysical Journal Letters, volume 996, page L34. It argues that the outer 15 to 20 meters of the comet's crust have been chemically altered over billions of years by galactic cosmic rays. These cosmic rays, very high-energy charged particles streaming through the galaxy from supernova remnants and other accelerators, slowly convert carbon monoxide locked into ice into carbon dioxide. Given enough time, this conversion would produce a CO2-rich outer layer. When 3I Atlas warmed during its approach to the Sun, that altered crust would be the first thing to outgas. The carbon dioxide we are watching, on this view, is the chemical signature of how long the object has been irradiated in interstellar space. The second explanation comes from the Cordiner team itself. It argues that the primordial composition of 3I Atlas, the way it formed in its parent stellar nursery, was simply different from the way solar system comets formed. The parent star might have been a thick disk star, an old low metallicity star formed during what astronomers call cosmic noon, around redshift 2, when the universe was perhaps 3 billion years old. The chemistry of that environment might have favoured carbon dioxide ices over water ices in the disk where this body coalesced. Both explanations are consistent with the data. Both have advocates. Neither has been ruled out. What is undisputed is that the carbon dioxide streaming off 3I Atlas, the gas JWST detected on the 6th August 2025, has not been part of any chemical environment we know. It was either built in a different galactic era, or it was modified by cosmic rays for so long that the modification itself becomes the message. Either way, the comet is old. This brings us to one of the most striking results of the entire 3I Atlas observational campaign. The age. In July of 2025, just 2 weeks after the discovery, a team led by Matthew Hopkins at the University of Oxford Department of Physics and Chris Lintott of Oxford and the BBC programme The Sky at Night presented a preliminary analysis at the Royal Astronomical Society's National Astronomy meeting in Durham. They had for some time been developing what they called the Ōtautahi-Oxford model. It is a kinematic statistical model that takes the velocity of an interstellar object and asks a specific question. Given everything we know about the dynamics of stars in the Milky Way, what is the age distribution of stars that move through our part of the galaxy with this particular velocity, on this particular trajectory? Stars in the Milky Way's thin disk, the young flat layer of star formation where most of the Sun's near neighbours live, tend to share roughly similar velocities. Stars in the thick disk, the older, dynamically heated population that surrounds the thin disk, move differently. They have higher velocity dispersions. They came from a different era of the galaxy's history. The Hopkins-Lintott team ran the trajectory of 3I Atlas through their model. The result presented at the meeting and posted as a preprint shortly thereafter was that the parent star of 3I Atlas was almost certainly in the thick disk. The age estimate, at 68% confidence, was between 7.6 and 14 billion years. Hold this for a moment. The universe itself is 13.8 billion years old. The Sun is 4.6 billion years old. If the upper end of this age estimate is correct, 3I Atlas was already drifting through the galaxy when the molecular cloud that would eventually form our Sun had not yet collapsed. The object may have spent more time in interstellar space than our entire planetary system has existed. A second paper, by Asta Taylor and Darrell Seligman, ran a different but independent analysis. It arrived at a slightly lower estimate, 3 to 11 billion years, but a broadly consistent picture. Old, probably thick disk, very probably older than the Sun. The light that left the surface of 3I Atlas in the autumn of 2025, the photons that reached the Atlas telescope on the morning of 1st July, and the JWST detectors on 6th August, had bounced off a body whose ices may have been frozen since before the first generation of long-lived low-mass stars in our galaxy had finished forming. Consider the scale. A solid object, smaller than a mountain, drifting alone through the galaxy for between 7 and 14 billion years, falling eventually, by chance, through the gravitational field of one particular yellow dwarf star, and by the smallest fluke of timing, doing so during a brief epoch when one species, on one rocky planet, had built telescopes that could see it. This is what was about to come closest to Mars. On the morning of 3rd October 2025, at 0438 Coordinated Universal Time, 3I Atlas made its closest approach to the red planet. The distance was 0.1937 of an astronomical unit, roughly 29 million kilometers, about 75 times the distance from the Earth to the Moon. For ground-based observers, this was a difficult moment. Mars and the comet were on the same side of the Sun, and from Earth, both were near the line of sight to the Sun itself, in the deepest part of the year when the inner solar system is hardest to image. But there are observers at Mars, 3 spacecraft, 2 from the European Space Agency, and 1 from NASA, were in orbit around the red planet that October. The ExoMars Trace Gas Orbiter, carrying the CASIS color camera and the NOMAD spectrometer, was operating on its routine science cycle. Mars Express, in orbit since late 2003, was running with its high-resolution stereo camera and its Omega infrared mapping spectrometer. NASA's MAVEN, in highly eccentric Martian orbit, was conducting its routine atmospheric observations with the imaging ultraviolet spectrograph. All 3 were redirected. For the first time in human history, 3 orbiting spacecraft at another world simultaneously turned their instruments away from the planet they had been built to study and pointed them at a visitor from another star. The images returned over the following days were not as sharp as ground-based observations. The cameras on those spacecraft were not designed for distant photometry. CASIS in particular is a high-resolution surface imager intended to map Martian terrain at 5 meters per pixel, not to track a faint moving point against the dark of empty sky. But what they collected was unique. From Mars, the geometry of the observation was different. The phase angle was different. The shape of the coma, the structure of the tail, looked different than it did from Earth. The Mars Express HRSC images would later be released by the European Space Agency in mid-October. A small fuzzy point surrounded by a soft halo, from a planet that had, until that moment, never had another visitor. 26 days after the Mars encounter, on 29 October 2025 at 11:45 UTC, 3I Atlas reached perihelion. The closest approach to our Sun came in at 1.35645 astronomical units. Between the orbits of Earth and Mars, the peak orbital velocity, measured against the Sun, was 68.3 kilometers per second, 245,000 kilometers per hour. By comparison, the Earth orbits the Sun at about 30 kilometers per second. The comet, swinging through the Sun's gravity, was moving more than twice as fast. It came no closer than that. It did not cross the Earth's orbit. It did not threaten anything in our neighborhood. It made its single, swift turn and began to climb back out. The photons kept arriving. There is a quality to comet observation that is worth pausing on for a moment. We do not really watch comets in real time. We catch up to them. The light reaching our instruments has left the object hours or sometimes days before, travelling at the speed of light through empty space, until it crosses our line of sight and is bent by our optics into a detector. Every measurement of 3I Atlas is, in the strictest sense, an archive of a moment already past. When the spectrum was taken at the Very Large Telescope on the 3rd of July 2025, the photons it analysed had left the comet roughly 50 minutes earlier. When JWST detected carbon dioxide on the 6th of August, the carbon dioxide had finished sublimating about 35 minutes before. The comet had already moved. The archive of light is older than the discovery. In the days after the Minor Planet Center released MPEC 2025 N12, astronomers around the world began searching their own archives. The question was simple. If this object had been moving through the inner solar system for months before discovery, perhaps it had been imaged by a survey camera that had not flagged it. The trajectory was now known. The brightness profile was known. The motion was known. With the orbit solution in hand, you could compute very precisely where 3i Atlas should have appeared on any given night during the spring of 2025, and then go look at the images for that night. The first major pre-recovery came from a team led by Davide Farnocchia at the Jet Propulsion Laboratory, working with Shantanu Naidu and collaborators, using data from the Transiting Exoplanet Survey satellite. TESS, launched in 2018 and designed to find planets around nearby stars, monitors broad swathes of the sky continuously. It does so in a wide-field photometric mode that is, in principle, sensitive to faint moving objects, even though it was never optimized for them. The team queried the TESS image archive for the region of sky that contained 3i Atlas's predicted positions in May and June 2025. They found it. In a paper posted to Archive as paper number 25, 07.21967, and published in Astrophysical Journal Letters volume 991, the team showed that 3i Atlas appeared in TESS images from the 7th of May through the 2nd of June 2025, 2 months before its official discovery. The object's apparent magnitude in TESS's broad red passband was 20.83 in early May, brightening to 19.28 by late May. Even more striking was that the comet had already been showing weak but detectable cometary activity at 6 astronomical units from the Sun. At a distance well beyond the orbit of Jupiter, where temperatures are too cold for water ice to sublimate, something was already coming off the surface. Probably carbon dioxide, probably the very same chemistry that JWST would later resolve in detail. A second pre-recovery came from the Zwicky Transient Facility, the wide-field survey running on the Samuel Oskine telescope at Palomar Observatory. ZEF images from the 22nd through the 29th of May 2025 also contained the object. The Weizmann Astrophysical Observatory in Israel had captured it on the 21st of May. Hold this for a moment. For nearly 2 months before discovery, photons from 3i Atlas had been arriving at telescope mirrors on Earth, photons shaped by the chemistry of a different stellar nursery, photons that had been travelling through silence for tens of thousands of years, and we had captured them. We had stored them in disks and databases and archives, and we had not seen them. We had not known to look. This is, in some ways, the quiet meaning of the archive. The universe is sending us light all the time. Not all of it has anyone receiving it on the other end. Some of it lands, is recorded, and waits for us to know what to look for. Now let us move forward in time to a second measurement happening continuously in parallel with the spectra and the imaging, the measurement of the trajectory itself. When the Minor Planet Center released its first orbital elements on the 2nd of July, they were based on roughly 30 hours of observations, 6 points on a single curve. As more telescopes contributed astrometry over the following weeks, the curve was refined. By the end of July, hundreds of observations were available. By the end of August, thousands. The Center for Near-Earth Object Studies at JPL, where Farnocchia's team maintains the running orbit solution, was updating the elements continuously. What this kind of orbit determination does is something called a residual fit. The team takes the known law of gravity, applies it to the predicted motion of the comet given the masses of the Sun and the planets, and then compares the prediction against where the comet actually appears on subsequent nights. If everything's purely gravitational, the residuals between predicted and observed positions are small, scattered noise around zero. If something else is acting on the object, a tiny thrust, a non-gravitational force, those residuals develop a pattern. The pattern is what astronomers call non-gravitational acceleration. By the autumn of 2025, the residuals on 3i Atlas were not zero. There was a small but real signal. The comet was not behaving as if pure gravity were the only thing pulling on it. This is, in fact, what happens with all active comets. When a comet warms in sunlight, ices on its surface sublimate, releasing gas. The gas leaves the nucleus preferentially in the direction facing the Sun, which acts like a small, steady rocket, pushing the nucleus very slightly away from the Sun. The effect is well understood. It is parameterized by what astronomers call the who developed the formalism in the 1970s. For a typical small comet, the non-gravitational acceleration is on the order of 100th of a millimeter per second. Tiny. Real. For 3I Atlas, by the time the comet approached perihelion, the radial component of the non-gravitational acceleration had grown to roughly 135 kilometers per day squared. The transverse component was about 60 kilometers per day squared. These numbers are not, on absolute terms, large. They are tiny compared to the gravitational acceleration of the Sun, but they were larger than a simple model of water ice sublimation, scaled to the size of the nucleus that Hubble had measured, would have predicted. The mainstream cometary community responded with a series of papers in late 2025. The leading explanation was that the comet's outgassing was dominated not by water, but by carbon dioxide. Carbon dioxide sublimates at lower temperatures. Carbon dioxide releases more mass per joule of solar input. And crucially, the dust grains carrying that gas off the surface were larger than the small particles that dominate typical cometary outflows. Larger grains, ejected at lower velocity, in greater bulk, generate more thrust per unit of mass lost. Combine the unusual carbon dioxide dominance with the dust grain population that Hubble and JWST had imaged, and the observed non-gravitational acceleration falls within expected ranges. There was, however, a minority position. Avi Loeb, of the Department of Astronomy at Harvard University, has spent the better part of a decade arguing that interstellar objects deserve a non-zero prior on the question of artificial origin. He developed this argument for 1I Oumuamua in 2017 and 2018 in a series of papers and in his book Extraterrestrial, published in 2021. For 3I Atlas, he wrote and posted to Arxiv a series of analyses arguing that the magnitude and timing of the non-gravitational acceleration near perihelion were unusually well tuned. He framed this carefully as a solar Oberth maneuver. The Oberth maneuver is a technique in spacecraft trajectory design, named after the German rocketry pioneer Hermann Oberth, in which a vehicle gains the most energy from a propulsive burn by performing it at the deepest point of a gravity well. Loeb's argument was that the observed accelerations, if interpreted as an engineered burn, would be efficient in exactly this way. The mainstream community responded carefully and thoroughly. Jason Wright, of the Pennsylvania State University Department of Astronomy and Astrophysics, who has worked on the methodology of distinguishing natural from artificial signals, published a detailed examination of Loeb's analysis on his AstroWrite blog in November 2025. The summary, distilled, was that every individual anomaly Loeb pointed to has a natural explanation grounded in the comet's measured properties, particularly its CO2-rich and dust-rich outgassing. None of these natural explanations require new physics. None require an artificial source. The Loeb preprints have not, as of mid-2026, been accepted in mainstream peer-reviewed journals. What is true, and worth stating clearly, is that the mainstream consensus is comfortable with 3I Atlas as a natural object. The minority position exists. The data, as measured, does not require an artificial explanation. The standard of evidence to overturn the natural cometary interpretation has not been met. This is what science looks like when it works. Disagreement, in public, on the record. A community that takes a strong claim seriously enough to examine it carefully, then sets it aside when the evidence does not support it. Now, let us return to the comet itself, on the other side of the Sun. In the second half of December 2025, after perihelion, after the swing through the Sun's gravity well, JWST observed 3I Atlas once more. This time it used a different instrument. The mid-infrared instrument, MIRI, can probe wavelengths between 5 and 28 microns. It is the only JWST instrument that operates in the mid-infrared, the range where many cold molecular ices have their fundamental vibrational fingerprints. The observations were taken on the 15th, 16th, and 27th of December 2025. The lead investigators were Jennifer Bergner of the University of California, Berkeley, and Daryl Seligman of Michigan State University, with collaborators from a range of institutions. The paper appeared in Astrophysical Journal Letters, Volume 1001, page L11. The MIRI spectrum showed something new. For the first time in any interstellar object, methane was detected. Methane, CH4, the simplest hydrocarbon. The same molecule that, on Earth, leaks from wetlands and bovine stomachs, and the gas pipelines of every industrialized nation. It was there in the coma of 3I Atlas, fluorescing weakly under solar ultraviolet light. The MIRI spectrum also confirmed water, now visible in its fundamental vibrational band at 6 microns. And it caught, in fine detail, the atomic nickel line at 7.507 microns, the same nickel that had been seen in the visible band by the VLT 5 months earlier. What this told the community was that the post-perihelion 3I Atlas was, in some sense, a different object than the pre-perihelion one. The outer crust, the layer that had been processed by billions of years of galactic cosmic rays, had been partly evaporated by the close approach to the Sun. Beneath it, fresher material was now exposed. Methane, more pristine ices, the actual primordial chemistry of whatever distant disk had assembled this body, was being released for the first time in our line of sight. We had not just observed an interstellar object, we had peeled it. Now, on the 19th of December 2025 at 6:01 Coordinated Universal Time, 3I Atlas made its closest approach to Earth. The distance was 1.7976 astronomical units, 269 million kilometers, roughly 700 times the distance to the Moon, and well outside the orbit of Mars. There was no danger. There never had been. The object was not heading toward Earth in any threatening sense. It was passing through the inner solar system on its own one-way path, and we happened to be in a part of the sky from which we could see it. For the public, this was the moment of greatest visibility. Telescopes around the world, professional and amateur, tracked it. Astrophotographers in dark sky sites in Chile, Namibia, and Western Australia recorded its small coma against the December stars. The comet, by this point, was glowing at around magnitude 11. Far too faint for the naked eye, but bright enough for a backyard telescope of modest aperture. Hold this picture for a moment. A 10-inch reflector in a suburban backyard, somewhere in the dark hills outside Tucson, all near the Canary Islands, pointed at a small smudge of light in the night sky. The smudge is, in some literal sense, the oldest thing the observer will ever see. Older than the Earth, older than the Sun, older than the long memory of every star they have ever named. And it is moving, slowly, against the background. The light is still arriving. The instruments are still measuring. The story is not done. By late January 2026, the comet had begun to dim. Its heliocentric distance had grown to nearly 3 astronomical units. Its angular separation from the Sun had begun to favour southern observers. The coma, which had reached a peak of perhaps 30,000 kilometres in diameter at perihelion, had compressed and stretched as the dust drifted into the tail. The major facilities, having captured the moments of greatest scientific yield, began to schedule less time on the object. The Hubble Space Telescope's WFC-3 made a final imaging run in early February. JWST went quiet on 3I Atlas by the end of January. The ground-based survey telescopes, including the Vera C. Rubin Observatory, continued tracking it. There is a quality to the end of an observing campaign that those who have been part of one will recognise. The high alert of discovery passes, the moments of rare measurement, when something must be done quickly, before geometry changes, before the object slips out of view. Those moments end. What remains is the long, quiet work of writing up what has been seen, archiving the data, and letting the object continue on its way. The instruments turn elsewhere. There are other targets. There is always more sky. The light kept arriving. Fewer eyes were watching now, but the photons did not know that. They left the comet, travelled across the inner solar system, and arrived at whatever mirrors happened still to be pointed in the right direction. Now let us follow the trajectory outward. I Atlas will pass closest to Jupiter on the 16th of March 2026. At 12:22 Coordinated Universal Time, the distance will be 0.3583 astronomical units, just over 53 million kilometers, close enough that Jupiter's mass will give the comet a small final tug as it leaves, slightly modifying the asymptotic trajectory by a quantity well within the orbit determination uncertainty. After that, the object will climb out of the planetary plane and accelerate in a relative sense toward the dark outer reaches of the solar system. By the year 2189, on its current course, 3I Atlas will reach the inner Oort cloud around 2,000 astronomical units from the Sun. By approximately the year 10,000 AD, it will cross the outer boundary of the Oort cloud and pass entirely out of our Sun's gravitational influence. It will not come back. It will resume its motion through the galactic disk, a small piece of rock and ice carrying photons from our star into the void, exactly as it once carried photons from a different star into our optics. This, for any astronomer who has worked on the object, is the strange end of the story. The comet is not lost. It is not destroyed. It will continue, intact, for billions of years more. It simply leaves. We will never see it again. We will never confirm any new finding about it. The dataset we have, by the spring of 2026, is the dataset we will ever have. Every paper written about 3I Atlas from now until the heat death of the universe will draw from the same finite archive of photons captured during a single passage. Now let us pull back from the object itself and consider what we learned from its passage. For most of human history, comets were our own. Every wandering tail, every Halley return, every Hale-Bopp dawn belonged to the cloud of debris that surrounded our Sun. They were built from the same molecular cloud that made the Earth in roughly the same epoch, around 4.6 billion years ago. They were old in the human sense, but they were local. In a paper published in Astronomy and Astrophysics in May 2026, archived at the European Journal portal under article number AA56405, Tim Hallett and Paul Wiegert performed a detailed galactic trajectory analysis of all three known interstellar objects. They traced the motion of 1I Oumuamua, 2I Borisov, and 3I Atlas backward through the gravitational potential of the Milky Way, using the most recent measurements from the Gaia satellite of nearby stellar populations and the galactic mass distribution. The result was striking. The three objects do not come from the same kinematic population. 1I Oumuamua's trajectory is consistent with a young, thin disk origin. 2I Borisov is intermediate. 3I Atlas comes from the thick disk, the older, kinematically hotter population of stars that were formed in the first few billion years of the Milky Way's existence. The three objects, in other words, sample three different epochs of galactic history. This is in some ways the deepest finding of the campaign. What it implies is that interstellar objects are not a uniform population. They are not all the same age. They are not all from the same kind of star. They sample the full diversity of planetary systems that have ever formed in the Milky Way. Every star that ever made a disk, ever made planets, ever lost some fraction of its outer ice to gravitational ejection during the chaotic phase of its planetary assembly contributes to this slow river of debris. Three samples, three epochs, three different chemistries. We are not looking at a galactic average. We are looking at a galactic census. Now let us ask the question that is, perhaps, impossible to answer. Where did 3I Atlas come from? In a paper posted to arXiv in September 2025 with paper number 2509.03361, a team led by Yuhan Guo and collaborators performed a systematic search for past stellar encounters that could have produced 3I Atlas. The method is straightforward in concept. Take the current trajectory of the object, the position and velocity vectors, measured to extraordinary precision by months of astrometric observations. Project the trajectory backward through galactic space, accounting for the gravitational pull of the Milky Way's mass distribution. Then look for stars whose past positions, also propagated backward through the same potential, intersect with the trajectory of 3I Atlas at a small enough distance and a low enough relative velocity to suggest that the star could have ejected the comet. The Guo paper found no convincing source. The trajectory of 3I Atlas traces back into a region of the thick disk populated by hundreds of millions of ancient stars, most of which are too faint, too distant, and too undermeasured to permit precise reconstruction of their past positions. The galactic potential, over timescales of billions of years, scrambles the kinematic information. The longer ago the ejection happened, the less you can know. Hold this for a moment. We have measured this comet with the most sensitive instruments in the human inventory. We have measured its volatiles to within a few percent. We have detected, in its coma, a fluorescing signal from atomic nickel that exists at parts per billion. We have constrained the size of its nucleus to within a few hundred meters. We have by now more than 100 peer-reviewed papers describing one piece or another of its composition, structure, and behavior. And yet, when we ask the simplest possible question, Where did it come from? The universe gives us nothing back. The information has been lost. The kinematic memory of the galaxy has stretched and faded across too many billion years. There is something that, for me, returns again and again when I sit with this fact. We are very good now at measuring what we can see. We are not good at all at finding what we cannot. The parent star of 3i Atlas may still exist, somewhere in the thick disk, slowly fusing hydrogen, quietly continuing its own long life. Or it may have already died, gone red giant, ejected its outer envelope, and faded to a slowly cooling white dwarf in some unphotographed region of the sky. Either way, it does not know. It has no record that one of its small icy bodies, billions of years ago, was kicked out of its disk. It does not know that the body wandered. It does not know that the body, after an interstellar journey of unimaginable duration, passed through the system of a different star and was, for a few months, the most watched object in the human astronomical record. The information is in only one direction. We measured the comet. The comet does not measure us. The parent star, wherever it is, does not know. Now, let us return to the chemistry. The carbon dioxide to water ratio of 7.6 was the single most anomalous measurement of the entire campaign. There is no precedent for it in any solar system comet ever observed. Cordiner and his JWST team, in their NIRSpec paper, framed it as a window into the primordial composition of a carbon dioxide-rich protoplanetary disk, perhaps assembled around an old, lower metallicity star at what cosmologists call cosmic noon, around redshift 2, when galactic star formation was at its peak. The argument is that in lower metallicity environments, with different elemental abundances and different temperatures, planetary disks build their ices differently than ours did. Maggiolo and his collaborators, in a paper published in Astrophysical Journal Letters, volume 996, page L34, in early 2026, proposed a different explanation. Their hypothesis is that the carbon dioxide-rich outer layer is not primordial at all. It is the consequence of billions of years of bombardment by galactic cosmic rays during the comet's interstellar voyage. The argument runs as follows. Galactic cosmic rays, mostly relativistic protons, accelerated by supernova shocks in star-forming regions across the disk, penetrate the upper meters of any small body in interstellar space. They break apart molecules. They drive radiation chemistry. Over a very long time, they convert carbon monoxide, which is the dominant interstellar ice in cold molecular cores, into carbon dioxide. The depth of processing is perhaps 15 to 20 meters. If Maggiolo is right, then what JWST measured, before perihelion, was not the comet's primordial chemistry. It was the comet's interstellar weathering. And the methane detected after perihelion, by JWST MIRI in December, was the first signature of the actual primordial interior, exposed for the first time in our line of sight by the heat of the sun. The two hypotheses are not yet decided. Both have peer-reviewed support. Both predict different things about future interstellar objects, which we will eventually be able to test. Now let us look to the future. The Vera C. Rubin Observatory on Cerro Pachon, in Chile, finished its commissioning phase in 2025 and began its full survey operations during the very year that 3i Atlas arrived. The observatory carries an 8.4-meter primary mirror, the largest active optics telescope ever built, and an LSST camera with 3,200 megapixels, the largest digital camera ever constructed for astronomy. Its mission, the legacy survey of space and time, is to image the entire visible southern sky every few nights for 10 years. What this means for interstellar objects is straightforward. The current discovery rate has been roughly 1 every 3 to 4 years, based on the cadence of 1i, 2i, and 3i. The Rubin Observatory's survey volume, sensitivity, and astrometric precision should increase that rate by 1 to 2 orders of magnitude. The expected yield is somewhere between 1 and 10 new interstellar objects per year, beginning, as the survey rises to its full operational tempo, around 2026, and continuing through 2035. What this means in scientific terms is that we are about to move from a population of 3 to a population of 50 or 100. We're about to move from anecdotes to statistics. We're about to have, for the first time, a sample large enough to ask demographic questions of the galaxy. What is the typical chemistry of an interstellar visitor? What is the typical age What is the distribution of stellar populations contributing to the flow of debris through our solar neighborhood? Ōtautahi Atlas will, in retrospect, be remembered as the last of the early ones. The third, the one that came before the catalogue grew large. There is a habit of mind that scientists sometimes acquire, the habit of regarding any particular object as an instance, not as itself. They learn this because the work demands it. You cannot do statistics with one object. You cannot ask universal questions of one example. You must hold the object lightly, as a sample drawn from a population, even if the population is only just being assembled. But there is also the other habit, the older one, the one that came before astronomy was a science. The habit of looking at a particular light in the sky and feeling somewhere in the back of the mind that this object, is unique. It has its own history. It came from a specific place, even if we cannot now name it. Its photons travelled a specific path, even if we cannot now reconstruct it. Its chemistry tells the story of a specific stellar nursery that may have already died, returning its mass to the galactic medium, leaving only a few pieces of debris drifting through the dark. The two habits live awkwardly side by side. Atlas will leave us. The data will be archived and gradually superseded. The catalogue will fill with successors. And yet somewhere in the record, the third interstellar object will remain itself. The one that came from the thick disk, the one with the carbon dioxide, the one that touched us briefly, in the year 2025, and then continued on its way. Now let us turn back to where we began, not to the present, not to the comet leaving us, but back to the night of the first detection. On the 1st of July 2025, at 5 hours 15 minutes and 11 seconds Coordinated Universal Time, in the dry high-altitude darkness above the small village of Río Hurtado, in the Coquimbo region of northern Chile, a half-meter survey telescope operated by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, pointed at a routine patch of the sky. The exposure lasted 30 seconds. The image came down through fiber optic cable into the system's automated processing pipeline. It was one of several thousand images captured by the network that night, distributed across telescopes in Chile, Hawaii, and South Africa, scanning the sky for objects that might one day pose a threat to Earth. There was nothing remarkable about the exposure. Hot pixels on the detector, cosmic ray hits, background stars in the constellation Sagittarius. The algorithm flagged a faint moving point of light at about magnitude 18.8, near coordinates that placed it just outside the inner asteroid belt. In the early afternoon of that same day, Larry Deno, an astronomer at the Institute for Astronomy of the University of Hawaii at Manoa, opened the night's catalogue of automated detections at his workstation. He was looking, as he had looked thousands of times before, for something that might warrant follow-up. The pipeline had given the candidate a temporary designation, 11PL3Z. The orbit-fitting code had failed to converge to an elliptical solution. The motion was too fast, the curvature too unusual. The pipeline had marked it as anomalous. Hold this picture for a moment. A man at a desk in an office in Honolulu, opening a file on his computer. Outside, sunlight. The everyday hum of an institution. Inside the file, an object older than the planet beneath his feet. An object that had crossed the dark, untouched by any star, for billions of years. That had entered the influence of our sun in late 2024. That had been picked up by an automated survey at 5:15 in the morning Chilean time, on the 1st of July 2025, and was now on this Tuesday afternoon in Honolulu, sitting in his queue. He did what astronomers do. He clicked through to the orbit determination page. He looked at the fit residuals. He noted the hyperbolic eccentricity. He sent the candidate to the Minor Planet Center for confirmation. Within hours, observers in Chile, Argentina, and South Africa pointed their own telescopes at the coordinates. The orbit refined. The eccentricity climbed. By the late evening of the 2nd of July, at 21:31 Universal Time, Minor Planet Electronic Circular 2025-N12 was issued, formally naming the object 3I Atlas, Comet C/2025-N1. I think about Larry Deno sometimes. I think about the moment on a Tuesday afternoon in early July when he was looking through a normal queue and saw a row of numbers that did not behave like anything inside the solar system. There was no fanfare, there was no music. There was a small, careful act of professional attention, and the universe on the other side of that act of attention was suddenly larger than it had been the day before. What still stops me about all of this, when I sit with it late at night, is not the chemistry. It is not the age. It is not the trajectory back into the thick disk, or the comparison to its older interstellar siblings, or the precise hour and minute of perihelion. Those things stop me too, but they are not the deepest part. What stops me is the asymmetry of the encounter. The comet does not know. The parent star, wherever it now is in the unmapped dark of the thick disk, does not know. The molecular cloud that gave rise to that star, long since dispersed back into the diffuse interstellar medium, does not know. The chain of physical processes that delivered this object to a survey camera in Río Hurtado, Chile, on the 1st of July 2025, runs in only one direction. The information arrives. It does not return. For some unmeasurable interval, longer than the existence of the human species, this small piece of an alien planetary system moved through silence. It passed through interstellar dust clouds that have already changed. It crossed the orbital paths of stars that have already died. Galactic cosmic rays, accelerated by supernovae that exploded before our sun was born, struck its outer crust and slowly altered its chemistry. None of this was observed. None of this was recorded. The comet kept its history only in the molecules and dust grains of its own body. It carried the record forward, unread, until the moment it reached an instrument that could read it, and we read it. We measured the eccentricity. We measured the velocity. We measured the volatiles, the metals, the spectral slope, the rotation period, the size of the nucleus. We pointed Hubble at it, and JWST at it, and the Very Large Telescope at it, and the Mars orbiters at it, and the new Vera Rubin Observatory at it. We extracted, in the span of a few months, a description of an object that had been silent for billions of years. We turned the comet from a piece of dark matter, in the older sense of the term, into a peer-reviewed entry in the human catalogue. Then we let it go. This, perhaps, is the part that I find hardest to put down. The comet did not need us. It would have continued on its hyperbolic course, whether or not we had built the Atlas network, whether or not Larry Dennew had been at his desk that Tuesday afternoon, whether or not James Webb had ever been launched. Our instruments were necessary for our knowing. They were not necessary for its passing. The object would have crossed our system in the autumn of 2025 either way, and would have left in the spring of 2026 either way, and would have reached the inner Oort cloud in the year 2189 either way. We are not the protagonists of this story. We are the witnesses. The story belongs to the object, and the object will not stop to tell us anything. There is a strange comfort in this for those of us who watch. Consider the scale. The Milky Way contains, by current estimates, somewhere between 100 billion and 400 billion stars. Each of those stars, if our solar system is any guide, formed inside a protoplanetary disk. Each of those disks, during its chaotic early history, ejected some fraction of its outer ices into interstellar space. The total population of interstellar objects in our galaxy, integrated over its 13 billion year history, is on the order of 10 to the 25th. 10 followed by 25 zeros. A number that, when you really hold it, does not behave like a number. It behaves like an ocean. We have seen 3 of them. We have seen so far 3 small dark bodies emerge from that ocean, cross our local current, and disappear again. The Vera C. Rubin Observatory is now operating. Its survey has begun. Over the next 10 years, we will likely see between 10 and 100 more. By the middle of the next decade, when this video has aged, when the technologies we currently use to make it are replaced by others, when even the names of our institutions may have changed, the catalogue of interstellar visitors will be larger than it is today by an order of magnitude. We will be doing demographics, not exclamations. We will be drawing histograms of chemistries. We will be asking, with increasing precision, what the galactic distribution of planet building actually was. I, Atlas, will not be among them. It will be a memory by then, a line in a database. The third one, the one we measured first with the kinds of instruments we had at the time, on the kinds of nights we had at the time. The light from 3i Atlas is still arriving, here in the spring of 2026. The Hubble Space Telescope is no longer scheduled to look at it. JWST is on other targets. The Vera Rubin Observatory is mapping new regions of the southern sky. The Mars orbiters have moved on. The comet continues outward, toward Jupiter, toward the outer planets, toward the Oort cloud, and beyond. In northern Chile, in the high-altitude darkness above the small village of Río Hurtado, the Atlas Survey telescope is still operating. It is still pointing, every clear night, at small fields of the sky on its regular cadence. It is still taking 30-second exposures. It is still flagging anomalous moving objects for human review. Most of what it sees is asteroids. Most of what it sees is already catalogued. But, occasionally, on some Tuesday morning, in some near future, the pipeline will produce a fit that does not converge to an elliptical solution. The eccentricity will refuse to settle below one. An astronomer somewhere, at a desk somewhere, looking at a routine queue, will see the numbers and pause, and the catalogue will gain a fourth entry, then a fifth, then a 10th, then a 100th. Each of them in its own way will be 3I Atlas. Each will be older than the sun. Each will carry, in the depths of its dust grains and ice mantles, the record of a planetary system that no longer exists in any recoverable form. Each will pass through our neighbourhood for a few months, be measured by whatever instruments we can train on it in the time it gives us, and continue on its way. The ocean does not stop. The river of debris keeps moving. We are inside it, not outside it. We have always been inside it. We have only recently learned to see it. There is one more thing I want to leave you with before this ends. When you look up tonight, or on the next clear night, or on any night that you happen to be outside in the dark and you see the sky, what you are seeing is not only what is there, you are seeing what has arrived. The photons from every star you can name left those stars long before the photons could know that you would exist to receive them. And among those photons mixed into the much larger flow of starlight, there are now, statistically, photons that have bounced off the surfaces of interstellar objects whose parent stars are dead. There are photons reflected from grains of dust ejected from systems that no longer have a sun. They are too faint to see with the naked eye. They are not labelled, but they are there in the small numbers, distributed across the field. Ōtautahi-Oxford Atlas by the late winter of 2026 is one of those sources. Its tail, illuminated by our sun, has been imaged by our telescopes. Some of the photons it scattered have already left the inner solar system, travelling outward at the speed of light, carrying a record of the encounter into the dark. 300 years from now, 10,000 years from now, those photons will still be moving, into volumes of the galaxy that we will never directly observe. Our sun's encounter with the third interstellar object will continue to broadcast outward, in the form of a faint wash of reflected and re-emitted light, long after the comet itself has passed beyond the Oort cloud. This is the strange parting gift of the encounter. The information that was lost in the deep past, the information about the parent star, the information about the molecular cloud that gave rise to it, the information about the system the comet came from, that information cannot be recovered. But the information about the encounter itself, the information about the visit, has now entered the galactic record. The comet came. The sun lit it. The light went outward. The light is still going. Now let us hold this for a moment, and then we will close. The third interstellar object passed through our system in the autumn of 2025. It was discovered on the 1st of July of that year by an automated survey telescope in northern Chile, and the discovery was reviewed by an astronomer at his desk in Honolulu. It was the oldest comet ever observed. It carried the most extreme carbon dioxide chemistry ever measured. It came from the thick disk of the Milky Way, from some star whose name we will never know, and it is on its way back into the dark, where it will travel for billions of years, slowly cooling, slowly losing what little volatiles it has left until it is indistinguishable from any other piece of debris drifting in the galactic medium. We measured it. We will not see it again. If this story stayed with you, a gentle like helps other patient listeners find this archive. There is more waiting for you in the playlist. Other objects, other distances, other questions that have outlived their askers. The catalogue continues. The river continues. The instruments continue. The light is still arriving. The telescope at Río Hurtado is still open. The question of where this object came from is still open. The third interstellar visitor is still this morning somewhere out beyond Mars, moving steadily, carrying with it the dust of an alien spring. And the universe, with its hundreds of billions of stars, continues to send fragments of itself across the dark, into the path of whoever, on whichever world, happens to be watching. Thank you for staying with me through this story.